Today we will be talking about our project for PH2102 electromagnetism. The topic of this project will be on electromagnetic pulses or EMPs. Our first focus will be on naturally occurring EMPs known as coronal mass ejections or CMEs. Next will be on man-made EMPs known as nuclear electromagnetic pulses or NEMPs. Today's world is highly dependent on electronics. Can you imagine if all our electronics suddenly went dark? Here we can see a quote by C.F. Herbert as he retells his experience of the Carrington event to the Daily News in Perth, Australia. It was a geomagnetic storm that triggered forest fires and set telegraph lines ablaze in 1859. Coronal mass ejections are bursts of highly energetic and magnetized plasma from the surface of the Sun. A typical CME takes about 3 to 4 days to reach the Earth. However, larger CMEs may just take a couple of hours. Before we talk about how the electromagnetic pulse is created, we'll take a quick look at the different states of matter: solid, liquid, gas, and most importantly, plasma. Plasma is a state of matter where the substance is an ionized gas. It is highly conductive, allowing electric and magnetic fields to influence it. Plasma can also achieve a condition where it is frozen in. In ideal situations, plasma achieves a frozen-in condition where the magnetic field is carried along with the plasma. When this condition breaks down, the magnetic fields are allowed to stray from the path of the plasma. Next, we'll talk about magnetic reconnection. Magnetic reconnection is a phenomenon which occurs when the plasma from the coronal mass ejections interact with the magnetosphere of our planet. Initially, the plasma from the coronal mass ejections are in a frozen-in condition and the magnetic field lines are coupled together with the plasma. However, as the plasma from the CME interacts with the magnetosphere of the Earth, the field lines become compressed. This results in the frozen-in condition breaking down, allowing the magnetic diffusivity of the plasma to increase. This then allows the magnetic field to release this pressure by shifting into a new equilibrium, ejecting plasma along the resulting outflow. This outflow results in a low pressure region which triggers continued outflow of plasma and magnetic fields, forming a runaway process of reconnection until the entire system re-establishes equilibrium. This rapidly changing magnetic field induces currents in electronic appliances on Earth. The induced current can overwhelm the power grid, causing blackouts and disruption to emergency services. Flights are also grounded due to the risk of electronic failure mid-flight. The CME can also cause satellites to malfunction and potentially fall back to Earth.
Next, we will talk about nuclear EMPs. But before we go into details, let's begin with an example. In July 1962, the USA detonated a 1.44 megaton nuclear bomb 400 meters above the Pacific Ocean. This nuclear weapons test was known as Starfish Prime, and was the first time the public experienced the effects of a nuclear EMP. The pulse knocked out 300 streetlights and tripped burglar alarms in Hawaii over 1,000 kilometers away from the blast site. Nuclear EMP starts with a detonation at least 100 kilometers above the Earth's surface. The nuclear fission that occurs releases photons that form gamma rays. These photons interact with the atoms in the atmosphere and displaces an electron, which is the phenomena of Compton scattering. With many atoms undergoing Compton scattering, this leads to a high number of electrons that move in a radial direction from the blast. NEMP is a multi-pulse electromagnetic radiation and has 3 types, namely E1, E2, and E3. Let's talk about E1 first. E1 pulse is fast but brief, occurring in less than a second of the blast and has a power of 50 kV per meter. The short yet intense E field induces high voltages in electrical conductors that exceeds the breakdown voltage of small components, leading to the destruction of computers and communication equipment. Next, we have the E2 pulse. Each pulse lasts from 1 millisecond to 1 second with a peak power of 0.1 kV per meter. It is the least damaging of the 3 pulses, and because it behaves similar to lightning, it is easier to protect against. However, E2 follows immediately after the E1 pulse, which means it can take advantage of the damage caused by E1 to the system to bypass defenses set up against it. Finally, we have the E3 pulse, the slowest yet most damaging of the 3 pulses, with each pulse lasting for tens of seconds up to a minute, with very high voltage. E3 can produce geomagnetically induced currents in long electrical conductors, which will damage larger components such as power line transformers. Why are high-altitude EMPs so dangerous? It is because of the area the EMPs cover. Like the example given earlier on Starfish Prime, the effects of the blast can be felt thousands of kilometers away. Imagine that we have no electricity. We can't communicate with our friends and family. We won't have light, nor will we have almost anything else. You won't be able to watch this video at all. Let's summarize. We've gone through natural and man-made EMPs. Both cause disruptions that affect us as we are so dependent on technology today. Thank you for watching, and we hope that this video has brought a better understanding of EMPs.